So you have a rescue team lifts an injured spelunker directly upward and out of a sinkhole by means of a motor-driven cable. The lift is performed in 3 stages, each requiring a vertical distance of 10 meters. Okay. So what we want to do here is we want to draw a picture for each of the three stages here. So it says initially he's stationary and he's accelerated to a speed of 5 meters per second. Then he is lifted at a constant speed of 5 meters per second. And then finally, he is decelerated to a 0 speed. Okay, so what are we doing here? We want to look at this from the language of the work energy theorem. So what do we see here? Note that in stages 1, 2, and 3, we have acceleration. So we have speeding up during stage 1, slowing down during stage 3. So that's really Newton's laws, if we could talk about that. So maybe we should start with the picture first. So let's sketch an image here. So if I sketch this thing here, I imagine that I have 3 stages. Maybe I'll do it over 2 squares. So this guy is number 1. Number 2, number 3 stage. And what you're seeing here, it says that he starts initially from rest. So I'm going to say, and then what's going to happen? Well, we know that he speeds up from rest to 5 meters a second. The only way we can do this is if there's a net force and the displacement are in the same direction. We are doing positive work during stage 1. And then what they say here is that you're speeding up to that interval to 5 meters per second. And then what happens? You're still moving with the displacement going upwards, but this time the net force is 0 because you don't change the speed, because they're telling you that when you get up to here, it's still 5 meters a second. So in this case, the work during this period is 0. And then finally, you're going to slow down to a speed when you get to the top that's 0. So that tells me that the only way I can decrease the speed here is if the net force and the displacement are in opposite directions. So the work during 3 must be negative here. So the question is, well, what has to happen here? So if I think in the language of a free body diagram, okay, so let's think about a free body diagram. We know that there's a cable that's moving the person up. So let's draw it here. So if you think about it, the only way you can move up here and speed up is that if I have the work of gravity has to be down, okay? Well, that means that the work of the cable, I said free body diagram. Ooh, that was a mistake. I should not say free body diagram. I'm thinking the workings. So then this has to be the work of the cable up. So the work of the cable has to be greater than the work of gravity, right? So in this case here, we're saying that the work of the cable during the first stage must be greater than the work of gravity. Then we get to the second stage. What actually has to happen? Well, in this case here, if there's no work being done, then the work going in has to be the same as the work coming out. So in other words, this work of gravity must be balanced by the work of the cable during stage 2. And when I get to stage 3, what we expect here, since we have negative work, then that means that the work of gravity must be bigger than the work of the cable in that stage here. So when I'm looking at this, I'm really saying these things right here. So in the language of energy, what I'm really saying here is that I have a system, right? And in each of these cases, I have a system. And what you're seeing in my system, right? You can see here is that the work, more work of the cable is going in than the work coming out due to gravity. And I'm trying to draw that bigger so you can see that there's difference. Because more work is being put into the system, that means I'm doing a bigger change in energy. So if I look at what happens next here, what's happening here is that the work being taken out by gravity must be the same as the work of the cable. So these guys are the same. But in order to reduce kinetic energy, what do I got to do? That means I have to take out more work of gravity than what the cable is putting in. So this is what I mean when I'm talking about energy flow. Note that this is quite different. It's different thinking. Why is it different thinking? Well, because when you look at this thing here, right? So what we're doing here is that we're changing our thinking from N2L to work energy, right? Because when I look at N2L, what does N2L tell us? N2L tells us that we're talking about mass times acceleration. But wait a minute, what is acceleration? Acceleration is about the change in velocity. And when you're looking at this change in velocity, what we're seeing here is that this depends on V. But now, if we're looking at the work energy term, what this tells us here is that the work is the change in kinetic energy. But we know that this guy is really about this guy depends on V squared. So clearly, these guys must be what? These are different thinking processes. So we have to change our picture. So if I look at this, and if I continue in this picture here, if I was to keep looking in this language here, here I go. What's the kinetic energy? Here I go. I know that the kinetic energy starts at what? Well, the kinetic energy starts at, how about if I do this in a different color? The kinetic energy initially starts at 0. But wait a minute, what do we know about the first case? We know that the work of the cable has to be greater than the work of the gravity. So then that means here, when I look at this here, I'm going to say that, yeah, there's work that's being done. So how much work am I going to be doing? Let's say you do this amount of work. So this is going to be the net work done during the first stage. And when you look at this thing, it looks like this. But wait a minute, how much did I change my kinetic energy? Well, I changed my kinetic energy by that amount. That's how much kinetic energy I did here. So now what happens? The same amount of work coming in is the same amount of work going out. So therefore, the work during this process here, right? The work during this process, during stage 2, well, that's 0. And look, I'm trying to set my bars to be all the same here in this scenario here. So now look at what happened to the kinetic energy afterwards. The kinetic energy at stage 2, the end of stage 2 is going to be what? Exactly the same. So then what happens next? We need to change the kinetic energy to 0. So that means here I have to do negative work. How much negative work do I got to do? Well, if this is 3 blocks, then I must do 3 blocks of negative work here. So I'm taking all of the kinetic energy out of that system, if we could say that. So that in the end, what we find here is that the kinetic energy at the end is K3 equal to 0. So there's a lot of ways to actually think about this. But now what we want to do here is that we can clearly see that what I got to do here is I got to go calculate what? The network of each of these things here. Let me make sure here. They're asking us to do what? How much work is done by the lifting force? Ooh, that's not what I was thinking the question was. But the picture doesn't change. So here we go. So in B here is that we want to calculate the work of the cable in each stage. Okay, so here we go. So let's start with our first stage, number 1. So what do we know here? From our picture, look what it says here. So let's be a little bit more careful here. So when I look at my picture here, we have an overall picture. Let's see what I'm really seeing here. Well, I have kinetic energy equal to 0. And look what I'm seeing here. There's more work of cable 1, and there's less work of gravity. So that means picture-wise, I'm going to say that this is how much gravity I have. And this is how much work I have of the cable during stage 1, right? So we're seeing this here. So now, picture-wise, I know that the final kinetic energy of this guy, so you could see that the red is 3, the green is 2. So then my purple tells me that I must have 1 square of that kinetic energy right there. So guess what? That's my equation right there. So let's apply the work energy theorem here. So from my picture, write out the work energy theorem. And so that means, look what I'm going to write. I'm going to write K initial minus the work of gravity plus the work of the cable of 1 equals K1. So how do I calculate this thing here? Well, for starters here, we know that K1 is what? 0. So I'm going to solve for the work of the cable. Okay, so solving for the work of the cable tells me here, you can see that the work of the cable of 1 must be what? The kinetic energy plus the work of gravity. But wait a minute, I know how to calculate the kinetic energy and the work of gravity because this is going to be 1/2 mv1 squared plus the work of gravity times my height change. So if I look at this thing here, if I look at what it says, the mass is 80 kilograms. The height of each stage is 10 meters, and the velocity at the end of that stage 1 is 5 meters per second. So then I just got to put that in. So then I'm going to get what? I want to get 1/2 times 80 times V1. So it's got to be 5 squared plus the work of gravity, which would be 80 times G times D, which is 10. And if you compute this, so note that this will all have units of joules. So if you compute this, I get 8.84 times 10 to the 3 joules, or 8.84 kilojoules for the work of the cable. So let's go to the second stage. So in the second stage, which I'll call stage 2, look what we're seeing here. The fact that there's no change in the kinetic energy, these two works must be identical. So let's go look at this thing here. So I'm going to go right off my picture now. So what does my picture say? My picture says this. It says, I'm now, look at my K1. I'm going to say that that's 1 squared. So my picture then says, okay, here's my K1. It's this much. So if it's this much, what am I going to do? I'm going to do 2 kinds of workings. I'm going to have the work of the cable, the work of gravity. Now, the weight of this cable shouldn't change. So the work of gravity should be exactly the same. So let's say that that is 2 squares. So I got to keep it at 2 squares. So that's the work of gravity. Now, we saw here that the work of gravity is always negative because it's trying to decelerate the system. It's trying to reduce the energy of the system. So then when I come in and I look at the work of the cable, what we're seeing here is that these guys have to balance out because we know that there was no change in energy of the system here. So picture-wise, if I have an equation and I see that K1 and K2 are exactly the same, that doesn't do anything, right? So the way I could write this, and I'll write it this way here. So then I keep going, right? I'm going to use the work energy theorem again. And this is what it says. It says K1 is positive. I get negative the work of gravity. I get positive the work of the cable. And that has to equal K2. But we know that these two did not change, so that they're equal to each other. So what do? I just cancel them out. If I cancel them out, what I'm really seeing here is that the work of the cable, 2, minus the work of gravity is 0. What a surprise. We knew that had to be the case. So just from physics, we knew that's the case here. So then it tells me that the work of the cable of 2 must be the work of gravity, which we already did the details upstairs, right, in stage 1. So then if I go in and I look at this thing, I know the mass, of course I know G and I know D. So if I come in and I compute this thing, again, I'm going to get the exact same as before. So it's got to be 80 kilograms times 9.81 times a distance of 10. So then this gives me 7.84 kilojoules. And that has to be the work of the cable at 2. Now, is this a surprise? Well, I could see that the work of cable 2 is smaller than the work of cable during stage 1. And again, from our picture, we knew that had to be the case. We looked at these things, and as we compare them, we knew that had to be the case. Okay, let's keep going on to the next stage. So if I go to stage 3, what's my picture now? Well, my picture knows that we're starting off at some high kinetic energy, K2, right? That hasn't changed. It's still the same right here. But this time, what has to happen? It's got to bring the kinetic energy to 0 now. So the work has to be negative here. So here I go. So now, where am I starting at? I'm starting at K2. Now, one of the things that might be useful is that we know that at the end, that the cable, that the kinetic energy at 3 must be 0. So right away, we could see here is that if that has to be 0, then the work of gravity, which shouldn't change, right? It shouldn't change. It still should be 2 squares because the weight of the cable, of course, did not change. So that means that the only possible way this could be true here is if the work of the cable has been reduced to, in this case, 1 block. So you could see that 2 minus 1 is going to give me 1 negative, and that's what kills off the kinetic energy. So by drawing these bar diagrams, we're actually writing down mathematical equations. So here I go. I need to calculate the work of the cable. So using the work energy theorem, for my picture, it's going to say what? It says K2 minus the work of gravity plus the work of cable 3 equals K3, but we know that's 0. So I got to solve for the work of the cable now. So solving for the work of the cable, then what I'm going to get here is I'm going to see here that algebraically I got to move everything to the other side here. So I have the work of the cable, then has to be the work of gravity minus K2. So let's go do that. And so what we're seeing here is that what's the work of gravity? Again, the exact same thing as before. And then kinetic energy is 1/2 mv2 squared. And note that we know what the kinetic energy is? Well, we calculated it before, but we didn't really write out a number. So let's just punch in our numbers again. So I know the weight. There's the weight, and I know the height. So that is the work of gravity. So now I got to put in the kinetic energy term. So it's got to be minus 1/2 the mass, and then I have 5 meters. I have 5 square joules. So when I compute that, I'm going to get a value of 6.84 kilojoules for the work of the cable. And 3. And so, as expected by just looking at energy flow, we could see here that the work of cable 1 during stage 1, that is largest. And then when we look at cable in stage 2, that's going to be next. And then the third stage is the smallest. So just by looking at what we were talking about earlier, this tells us here that the work during stage 1 is greater than the work of the cable during stage 2 and the work of the cable during stage 3. So it's exactly what we expected by looking at this from energy flow here.